So let's finish the derivation for surface area of revolution. We said we have some curve C. It is revolved around the x-axis and it creates a surface. We want to find its area. Okay, so what I did is I took the interval. This is the x interval from A to B. We partition it. We divide it into sub-intervals. And here I'm taking the first term over the k interval here, xk minus 1 to xk. And the area of it depends on the slant height, which we call delta s. Again, this is just an increment of a length, the lower radius and the upper radius. Okay, so you take 2 pi times the sum of the two radii. The lower radius is the value of the function at xk, and the upper radius is the value of the function at xk minus 1. Okay, and you multiply that by the slant height. Okay, I have the slant height in green over here. All right. And then to get the total of the areas. So again, we have n of these surfaces. Okay, we've partitioned the interval. We have n of these objects or surfaces. Okay, to get the total area, you do a sum. And that gives you an approximation to the area of the surface. Okay, so here S, surface area, is approximately equal to the sum where K goes from 1 to n, okay, because we've partitioned into n sub-intervals of the formula for area. It's 2 pi times f of x sub k minus 1 plus f of xk times delta times the slant height. Again, this is the little s. Little s is length, big S is area. All right. Yeah, and to get the exact surface area, we have to take n to infinity. You do the limit of the what's called the Riemann sum. Limit as n goes to infinity of the sum. Okay, because, well, you know why. You have the more and more of these first terms you have, the better is approximation for your area. All right. Now let's see what happens when n gets big. When n getting big means that the number of subintervals, basically your partition, is going to go to infinity. Okay, you're going to have more and more of these subintervals. Okay, so here you could have, let's say, 10 of these or any of those. But the more and more of these subintervals you have, what happens is that the length or the width of each subinterval is going to get small. See what I mean? And just imagine we have more partitions. The endpoint of subintervals become closer and closer together, right? The width of the subintervals goes to 0. And as that happens, here this xk minus 1 and this x sub k, again, they get closer. They get closer to each other and they eventually become a single point. And you could just assume that single point is this xk star. Okay, let me write it down. Okay, so as n goes to infinity, again, which means more partitions, both x sub k minus 1 and x sub k approach that sample point, x star sub k. Okay, which means that f of xk minus 1 gets closer to f of xk star, and f of xk also goes to f of xk star. Okay, that gets close to that, that gets close to that. Or
So
it gets,
is x k star the midpoint or just a point between those two points?
it doesn't have to, it could be midpoint, it's up to you. You could choose it to be whatever you want, but it doesn't have to be midpoint.
Okay.
It could be any point in between. As a matter of fact, you can make xk minus 1 go to xk, or you could take xk, go to xk minus 1, or you could have both of them go to the midpoint. When you do Riemann sum, if you remember from Calc 1, you can take the left endpoint, you could take the right endpoint, you could take midpoint. Okay, but we'll just generalize and say they both go to that. All right, so when that happens, these two y values get close to the y value that corresponds to xk star. Okay, these both go to xk star, so their y values go to f of x sub k star. My k's are weird here. Okay. Yeah. So what happens is that since these become the same thing, right? These become the same thing, these two. So you end up with two of them. We could write the limit this way. Limit as n goes to infinity of the sum 2 pi times 2 f of x star k times the increment of arc length. Okay, and what this is basically an integral. This is a definite integral. The limit of a Riemann sum is the integral. If this is the integral from a to b times I'm not sure why I have, let me see, let me go back. Going way back, here the 2's canceled out, didn't they? those twos canceled out. So I don't know why I have a 2 here. No one said anything. Okay. I made a very obvious mistake I wasn't supposed to make. So that 2 was not supposed to be there right from the beginning. But again, these both become the same thing. They both becomes f of x star k. So you have 2 f of x star k's. And the limit of the Riemann sum is the integral from a to b times 2 pi. Basically, f is just your function y. Let me also write that in a different color so you can make the association. Okay, so 2 pi times y. And then if you remember, this is just arc length increment. That is arc length increment, which is dx dt squared plus dy dt squared times dt. Okay. And okay, well, I guess I wrote the parametric form of the arc length here, which is which I have to go back and make a tiny correction with my a and b here. A and b are t values, okay? These are t values because I wrote this integral in terms of t. But right here, my a and b, these are x values. So this, instead of being a, that's x of a. That's x at a, and then this is x at b. A and b are time values, guys. Those are t values. All right, so yeah, this is the parametric form of surface area. The non-parametric form of it is done somewhere in chapter 7, I think, or chapter 6 or 5, I don't know. But you just do the integral of the integral 2 pi y, 2 pi y. That's, think of that as 2 times pi times radius. Y is, if you take like a cross section like that, y is the radius. So think of this as circumference times the increment of arc length. You can remember it that way. All right. Now, this is when C revolves around the x-axis. Okay. If C revolves around the x-axis, then the radius is y. But if C revolves around the y-axis, can you tell me how this formula should be modified? Anyone?
Should be x instead of y.
Yes, we have x instead of y. If like, let's say this goes around, then this would be the radius. And that distance is x. I'm not sure if the book does problems with revolution around the y-axis, but in case. So let me write the theorem down, the surface area theorem. We'll just do it here. This is just arc length. It is like arc length, the statements with a couple of extra requirements. And it says, let C defined by x equal to f of t and y equal to g of t. Those are your parametric equations. Be simple or again closed simple on the t interval from a to b. Okay, and also we want C to be smooth. but not unclosed, but open interval AB between A and B. Okay, with an extra requirement, we are talking about area here, guys, area. And for area, area is a non-negative quantity. It's a positive quantity. You want this y to be non-negative, okay? If this function is negative, then you're not gonna get area. You're gonna get a negative integral. The integral of a negative function is going to be negative. Okay, so we want that y to be non-negative on the interval AB. Okay, then the area when C is revolved around the x-axis, again, is 2 pi. I'm taking the 2 pi out times the t integral from A to B of y times x dot squared plus y dot squared, and integration is with respect to t. Okay, so again, we need smoothness and we need C to be simple because of, well, smoothness is needed because of the arc length increments. These have to be defined and this should not be 0. Okay, and again, if C is not simple, if it overlaps or intersects, then you're gonna get overestimates. You're not gonna get the area. You're gonna get something more than what you should get. All right. Okay, so let me just write it down. If assuming x is greater than 0 on AB, area when C is revolved around the y-axis is same thing, but here again we have x times the increment of arc length. Yeah, of course, this time x has to be greater than 0 because the radius is supposed to be x, the distance from the y-axis to a point on C. Example, let's look at the area of a sphere. So how do we get a sphere? We take a semicircle and we revolve that around a horizontal axis or a vertical axis. Okay, so the parametrization for a circle of radius A is again A cosine t and y A sine t. Okay, again, here A is positive, and the t here goes from 0 to pi. Okay, that gives us a semicircle. We don't need to take a full circle and revolve that around the x-axis. It just doesn't make sense. Like imagine we have a full circle, okay, then C is sometimes negative, and that's not what we want. Like down here, C is negative. So take your t from 0 to pi, and that gives you a semicircle. Okay, so again, this is revolved around the x-axis to generate a sphere. And we're going to find the surface area. Okay, we've already checked smoothness, and we know that this curve is simple on 0 to pi. Oh yeah, Jose is mentioning that. And we know that this is the upper semicircle anyway. So C is positive. Okay, this is the parametric. This is the parametric function. Functions graph, that's your curve. And it's positive. This is always above the x-axis. So your y is greater or equal than 0 on 0 to pi. All right. We've already checked the requirements. So let's find the surface area. First of all, again, you need to calculate your x dot, y dot, x dot. We've done this already twice. X dot is negative a sine t, that's dx dt, and dy dt is a cosine t. Square those at that gives you again a squared sine square t plus a squared cosine square t. And again, this is just a squared. Pythagorean theorem, Pythagorean identity for trig. All right, and use this information to set up the integral. So the integral again is 2 pi times the integral from a to b of y times, again, the arc length increment, and integration is with respect to t. Okay, so we have 2 pi. The integral is going from 0 to pi. Y here is right there in front of you. Y is a sine t. Okay, and we have the square root of a squared. Not a bad integral at all. If you're gonna do this in non-parametric form, you're gonna have a little bit of trouble with the integral, okay? Because in non-parametric form, the equation of the semicircle is y equal to square root of 1 minus x squared. You have to take the derivative of this. You have to plug it into the non-parametric form of surface area. You can look at a formula in chapter 5 or 6. Okay, the integral is going to become very, very ugly. Well, it's not going to be that ugly, but it's not going to be as nice at all. As a matter of fact, when you set up the integral, you're going to have to do a trig substitution, I believe. Okay, but this takes the parametric form of it takes care of the integral. It makes it simple. Square root of a squared is a. It's a constant times that by this a. You get a squared. You can kick that a squared out of the integral. Get 2 pi a squared. The integral of sine t is negative cosine t. Evaluate from 0 to pi. Make sure you end up with a positive value. Okay, so 2 pi a squared, plugging plugging pi in, we get negative of -1. And then we have minus negative cosine, so that's plus cosine of 0, which is 1. Okay, that the bracket is 2. You have 2 times 2 pi squared. That's 4 pi a squared, square unit. Four pi radius squared. That's the surface area of a sphere. 4 pi radius squared. You can look it up. 4 pi radius squared is area of a sphere. All right. So questions? You can do a lot of fun stuff with this thing. You can take a circle and like let's say you have a shifted circle, like shifted up by shifted so that its center is, let's say this is whatever. Let's say we have a circle like that. If you revolve that around the x-axis, it will generate a donut, and then you can find its surface area. Okay. But no questions?
Yeah, Professor, can you
Yeah.
explain how you got a squared in that like final step again?
This a squared?
Yeah.
Right, so here we have, at this step, we have a over here, and here we have square root of a squared. This is a, and then I multiplied a by a, that's a squared. I wrote it right here.
Oh, okay, okay, thank you.
And then just, it keeps carrying over. All right, so think about this. If you have questions, let me know. I am gonna set up the notebook for the next lesson. We are finally done with this section, guys. Yeah, just give me a few seconds. Next section is really cool. We're gonna be looking at a different coordinate system. Okay, so far we've been working in what is called the Cartesian system or the rectangular system. Okay, since what, first grade till now. Did you guys hear that?
Yeah.
Someone just dropped something right above me, upper floor. Damn. I thought it was an earthquake. But the Cartesian system or the rectangular system that you guys been working with since day one, you're just dealing with x-axis, the y-axis. Okay, you have east, west, north, south. So this is section 10.3. It's called the polar coordinate system. Yeah, so the rectangular coordinate system, or also known as the Cartesian. Every point is represented by x, y. It sounds like a wrestling match. Yeah, so we assign in this system, we assign x, y to every point in R2. Okay. Again, X is basically east-west, Y south-north. Okay, left, right, up, down. And that's what we are used with, what we are used to since first grade. Okay. The thing is that when people wanted to study certain geometry, okay, like the movement of, like let's say you want to study certain geometry on a surface like a sphere, right? A sphere is round, it's not flat, right? It's not flat. So assigning an xy is kind of difficult, right? Xy is good if you're in a flat space, but if the space or the surface is not really a flat plane, like you have surface of a sphere or a cylinder, then doing Cartesian type of work is not easy at all. It's not. So people came up with a different coordinate system. It's called a polar coordinate system, where we don't address a point using xy anymore. Okay, so to understand the polar coordinate system, well, let's talk about the polar plane. Okay, so we have the plane, the xy plane. When you learn how to work in R2 in second dimension, you were introduced to the xy plane, right? So we have to know what a polar plane is. Okay, let's say we have some point O be a fixed point in R2 in space. Okay, so here is O. Right, we typically use O for origin, 0, 0, or O. Okay, take any point Q. That is not the same as O, of course. To form the ray PQ, this is a ray. A ray is a half line. So let's say here is Q. We'll connect those to form a half line or a ray. All right. So in the XY plane, with the XY axis, we have the x-axis, we have the y-axis. Those are called the coordinate axes. This is the polar axis. We don't have x-axis and y-axis. We have a polar axis, and the polar axis is just it. It's a half line. Okay. It's basically the same as a positive x-axis. Okay. Here we call this pole. And this ray PQ or the ray OQ, I'm sorry, guys, I don't know why I said PQ. OQ is what I meant to say. Yes, OQ. Yeah. The ray OQ is called the polar axis. Okay, so when we work in polar space, all you need, frankly, is just a half line. And I'm going to show you what a polar grid is later on. We'll make the polar plane a little nicer, but OQ is all you need, a half line. Okay, now, how is a point in flat space or in space represented using the polar coordinate system. Take any point, call it P. In R2, let's say here is that P. All right, again, we want to know how to describe that P or how to address that P. I don't know what's wrong with this pen. Okay, so P can be described using so again, in Cartesian system or in rectangular system, P takes on an X and a Y. Okay, in polar system, P takes on what's called the directed distance, which we call R. Okay, R is basically this. This is R, the distance from O to P. Okay, and that distance can be directed. I'll tell you guys what that means. So directed distance. By directed, we mean that this distance can be either positive or negative. I know distance can't be negative, but in polar system, it could be negative. So directed distance plus or minus from O to P. Okay, for now, just think of R as how far that point is away from the pole. Okay, and we also need direction. We have distance, we need direction that can be described using this angle here. So, theta, which is the directed angle. My dogs are going crazy. Hold on, guys. Dogs freaked out so bad because of the noise from above, but sorry about that. So question from AJ, wait, it can be negative for polar? Yes, it can be. Yep. We could have a directed distance. I know, it's interesting. Okay, and we have a theta, which is also what's called a directed angle that the segment OP makes with the polar axis. Okay, so a point can be addressed by, again, how far that point is away from the pole and the angle that this segment makes with the polar axis. No more xy, no more x and y. Instead, we have r theta. Okay, so let's talk about this word directed. What does that mean? What does it mean for an angle to be directed? All right, so yeah, by the way, angles here come in radians. We don't typically write the theta value in degrees. We write it in radian form. All right, so here what you do is, again, draw the polar axis. Okay, that's your pole. All right, all you have to do is go counterclockwise by 45 degrees. I'm just going to draw that as reference. Go by 45 degrees. So bisect the 90-degree angle. That is, we go that way by pi over 4. Okay. And then in that direction, we go basically 3 units in the direction of the terminal site. That is the terminal site of pi over 4. Go 3 units. 1, let's say 2, 3. Okay, and there is the location of P1. Very simple, I hope. Okay, second point. Let's say P2 is also 3 for R, and let's say we go with 9 pi over 4. Go crazy. Can anyone tell me what 9 pi over 4 is coterminal with? What angle is that coterminal with? Pi over 4. Yes, 9 pi over 4 is 2 pi plus pi over 4. My wife just called the landlord and started yelling at her. I could hear the whole thing, shenanigans. All right, so 9 pi over 4. Again, to locate 9 pi over 4, just go around. We go around counterclockwise. That's a positive value. Go around a 2 pi. That's 2 pi, and then, oops, that was not supposed to happen. When you hold the pen for too long, it automates things. So 2 pi in addition to pi over 4, extra pi over 4, that is the terminal side. Okay, the reference angle is really pi over 4. We say 9 pi over 4 and pi over 4 are coterminal. They share the same terminal site. And again, in that direction, just go 3 units. Okay, 1, 2, and 3, and we have P2. Okay, so the point I'm trying to make here is that P1 and P2, guys, have 2 different addresses. P1 and P2 are the same point, but with 2 different addresses. We can actually come up with addresses that have a negative var. We'll do that in a little bit. But the point I'm trying to make is that the address to a point in polar system is not unique. We didn't have such thing in rectangular or Cartesian system. Every point in Cartesian system has a unique address. Okay, so for example, this is your x-axis, y-axis. That point is just 1, 2. There is no other way to address that point. But that's not the case here. You can have, as a matter of fact, infinitely many addresses for a point. You can go, instead of 2 pi, you can go 4 pi plus pi over 4, get a different angle for the same point. All right, let's look at another address to the same point, but with a negative theta. Okay, so 3. I'm basically going to, we're going to be drawing the same point, but with different addresses. So here, P3, third point. Let's say our here is 3 and theta is negative 7 pi over 4. Okay. Do you guys know where negative 7 pi over 4 is?
Same place as pi over 4.
Yes, exactly. So again, draw the polar axis. Okay, 7 pi over 4 in the clockwise direction. All right, if you remember from basic trig, when you go clockwise, that would be negative pi over 4. Okay, this would be, if I keep going, that angle would be negative 3 pi over 4. Okay, this would be negative 5 pi over 4. And just keep going clockwise, this would be negative 7 pi over 4. Okay, so 7 pi over 4, if I actually have my unit circle here, I was teaching my pre-calculus class yesterday, and I should have my unit circle. Come on. Yes, there. All right, so going counterclockwise, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Again, we measured that way. Okay, going clockwise this way, this is negative pi, just go with the same sequence, but backwards, negative pi over 4. That's negative 3 pi over 4. Negative 5 pi over 4. Negative 7 pi over 4. So negative 7 pi over 4 and pi over 4, they share the same terminal site. They're co-terminal. So that is the terminal side of that angle, and again, measure 3 units in that direction. Let me do that again. Good enough. So 1, 2, and 3. There is the location for P3. Okay, P1, P2, P3, they're all the same points. Again, different addresses. Let's come up now finally with a address with a negative R for that point. Okay, I'll just tell you what the address is. Let's call it P4. P4 is negative 3 for R. And let's say 5 pi over 4 for theta. Something really strange about the way polar points are written. Notice that we first locate the angle, right? I first measure the angle and then we'll count our units. So I wish whoever came up with the polar point system, they had theta and then R. It is R theta. I don't know why. That just doesn't make any sense to me. Makes no sense. Why it's not theta R instead of R theta. Okay, so 5 pi over 4, that is in the counterclockwise direction. Okay, so if I go in the counterclockwise direction, that would be pi over 4 This would be 3 pi over 4. This angle would be 5 pi over 4. Right? Again, I hope your basic trig is good enough. So we go again, counterclockwise. That is the terminal side of 5 pi over 4. It's in quadrant 3. And then, yes, this is the terminal side, all right? If r was positive 3, then you go 3 units that way. But r is negative 3, so you don't go in that direction. You go in the 180-degree opposite direction, which would be the other way. Okay, gotta go that way by 3 units. And there is your location for P4. So this is negative 3.
Wait, Professor, why isn't it the other way? Like
R
Well,
is
isn't-
negative.
the
R?
the -3, why is it like in quadrant 1?
Yeah, so if this was a positive 3, just like before, you measure your theta and you draw the terminal side. Okay, go 3 units on the terminal side. Okay, if r was positive 3, but
Mhm.
if r is negative 3, instead of going over your terminal side, you go the opposite. You go the
Okay.
opposite. That's
Yeah.
what a directed distance means. You go the opposite, the 180-degree opposite of your terminal side, which would be that way instead. Okay, so this point here would be 3 5 pi over 4. And this point that we just drew is -3 5 pi over 4. You get it?
Yeah, okay, thank you.
So once more, guys, there are so many ways that we can come up with the address for a point. An address is not unique. Okay. All right. So next time you come back, we'll continue. There's just a lot more to do with polar system. I'll see you guys on Monday. And I'm gonna email you guys about the test. Okay.
Thank you.
We're gonna hold the test sometime next week. I'll email you.
Thank you, Professor.
You're welcome. Have a great day.
Thank you, Professor.
You're welcome.
Professor, just a quick question about exam number